In this video, we're going to talk about Hess's law. So Hess's law is pretty much like another method of finding the enthalpy change. You probably have done the bond energies and the standard enthalpies of formation. These were all like another method of finding the enthalpy change, and Hess's law is no different than that. It's a method to find the enthalpy change. So according to Hess's law, the enthalpy change of a reaction depends only on the initial and the final condition of the process. The enthalpy change of a multi-step process is the sum of the enthalpy changes of its individual steps. So in short, to find the enthalpy change of this reaction, we need to somehow rearrange these equations here, and we gotta make sure that the net equation is the same as this, and if they're the same, we can simply just add these up, and that will be our enthalpy change of this reaction. So now I'll just label the reactions here. So this is reaction 1, reaction 2. Okay, so now to begin, the best way to do is to try to pick a reactant that's unique. Okay, so for example, in reaction 1, NO is unique. Notice that it doesn't show up in reaction 2. It's unique, so we can use that. And now we need to somehow rearrange so we can get something like this. We see that NO is on the reactant side, but however on the original equation the NO is on the other side, the product side. So what we need to do is reverse the equation and then multiply by 2, because here there's 2 moles of NO while here there's only 1, the coefficient. So you'll have to multiply by -1 whenever you're reversing the equation, and then you'll also have to multiply by 2, so times 2. And if I just write the new equation right there, it's going to be, so the NO, so I'm going to reverse it and then double the equation, so I'll have just 2NO2 because I doubled everything, and the NO2 is on the other side, and then this will form 2NO plus, and then half times 2 is just 1, so that's just O2. This is our first equation. And now for the second equation, we need to choose something that's unique. And notice that this is unique because it's not in the equation 1. But if we choose oxygen, there's going to be a problem because oxygen is also in the reaction 1. So N2, like nitrogen, is a better option. So we see that nitrogen here is already on the reactant side. But however, the coefficient is different. Notice that this one is just 1. This one is just 1/2, the coefficient. So we only need to multiply by 2, the whole equation. So I'm going to multiply by 2 here. So then our new equation here is going to be, so 1/2 times 2 is just 1. So it's just N2 plus, and then O2, so times 2. So you just have O2, like 2O2 here. And then this is going to give 2NO2. And now we simply just add them up. So we see that this and this cancels out. 2NO2 and 2NO2, they're on the different side. Okay, they're on the other side. And now this one, the oxygen here cancels out, and here the coefficient cancels out. So now our net equation is just N2 plus O2, because 2 minus 1 is just 1, and then this gives 2NO2. Notice that this is the same as the equation above, so therefore we are on the right track. And now that the equations are the same, we can just simply add these up. And you need to make sure that you first multiply by all the adjustment that you did and then add them up. And now here we just need to add them up. So the enthalpy change was just negative 56 kilojoule, but however we made some adjustments, so we multiplied by -1 and then multiply by 2, and then we'll add it with another one, so that's delta H is 34 kilojoule. And here the only adjustment we made was multiplying by 2. So now add these up on your calculator. So this gives me, so here I get 180, so therefore the enthalpy change of this reaction is 180 kilojoules. Now let's try this problem here. So we have to find the enthalpy change of this equation here again. So we'll begin in reaction 1. So in reaction 1, N2 is also found in reaction 3, so this is not unique. And O2 is found in reaction 2, so we can't use that. But however, NO2 is not found anywhere else, so we can use that. But however, NO2 in reaction 1 is on the product side, but however on the original equation is on the reactant side, so therefore we must multiply by -1 to reverse the equation. And now we have to look for the coefficient. So in reaction 1, the coefficient of NO2 is simply just 1. But however, on the original equation, it's 2. So we have to multiply by 2 to get there. And now we can just write this equation here again. So we have to reverse the equation. So this is the first thing that'll show up. So NO2 times 2 is just 2NO2. And then this will form. And then O2 times 2 is just 2O2, and then plus a half of nitrogen times 2. So a half times 2 is just 1, so this is just N2. This is our first equation here. Now for second equation, hydrogen is found in reaction 3, so it's not unique. And oxygen is found in equation 1, so it's not unique. But however, H2O is unique because it's not found anywhere else. And H2O is on the product side. But however, on the original equation, it's on the reactant side. So we have to multiply by -1. And now the coefficient of H2O here is just 1. But however, on the original equation, it's just 2. So we have to multiply by 2 to get there. And now we'll simply write the equation. So we reversed it and then multiplied by 2. So H2O times 2, so 2H2O give 2H2 plus, and then half of oxygen times 2. So a half times 2 is just 1. So this is just O2. That's our second equation. Now for the third equation, nitrogen is found in step 1 again, so it's not unique. And same with hydrogen, found in step 2, so we can't use that. But however, N2H4 is found nowhere, so this is unique and we can use that. And notice that This is on the product side, and same with the original equation, it's also on the product side. And if you look at the coefficient, they're just both 1 and 1, so they're the same. And since they're the same, we do not need to do anything else because they're already there. So you can just simply copy this equation over here if they're the same. So N2 plus 2H2, this gives N2H4. This is our equation, and now we simply add them up. So look for something that you can like cancel out. Notice that I can cancel N2 and N2 here, and then 2H2 and 2H2 I can cancel that here, and it looks like that's it. And now I'll add them. So this side I'll add these, so that's gonna give our net equation. It's just going to be 2NO2 plus H2O, and then I don't have enough space, I'm just gonna like put an arrow down here and then write a new one here. So, and then this 2 plus 1, that's just 3O2 plus this thing, this, so it's just N2H4. Notice that we have this the same as the original equation. Our net equation is the same as the original equation, so now we can simply add them. We're on the right track. So now our H total is just going to be the sum of all these. So 33.2 times -1 times 2 plus -241.8 times -1 times 2 plus 47.6, and yes, the units are in kilojoules. So the total enthalpy change is, which should give 464.8 kilojoules. This is the enthalpy change of the reaction here. Now try this example by yourself, and yes, feel free to pause the video and let's begin. Reaction 1. So zinc oxide, let's see if zinc oxide is unique, and it is not found anywhere else. And zinc oxide is on the reactant side, but however on the original equation it's on the product side, so therefore I must multiply by -1, and the coefficient are the same, it's just 1 and 1, so I'm just multiplying by 1, but I don't really need to if it's just because it's the same anyways. And now with reaction 2, sulfur is found also in reaction 3, so it's not unique. And oxygen is found in reaction 1, so it's not unique. But however, sulfur dioxide is unique because it's not found anywhere else. Notice that sulfur dioxide is in the product side, and so is the original equation. It's also in the product side. And the equation, the coefficient is just 1 and 1. So they're the same, so I do not have to do anything. It's the same. I do not need any sort of rearrangement. Let's move on to 3. Zinc sulfide is not found anywhere else in the equation, so therefore I can use it here. And zinc sulfide is in the reactant side, and so is the original equation. It's also on the reactant side. And with the coefficient is 1 and 1. So it's the same here again. So I do not have to do anything here. Here, these are going to be the overall equation after doing rearrangement. So I only multiplied the first equation by -1. So I'm just reversing the first equation only. It's going to be Zn zinc plus half of oxygen, which gives zinc oxide. That looks like a U for some reason. And now the second equation here, I just leave it, so it's going to be sulfur plus O2. That's going to give sulfur dioxide. And then the third equation is the same as well, so zinc sulfide, which decomposes into zinc plus sulfur. By the way, you only cancel out when the same element or molecule is found in the reactant side and the product side. So for example, here zinc cancels out with the zinc here because this is in the product side, but this is in the reactant, so they both cancel out. And with sulfur, I could cancel this out here, cancel that out. And that's really it. And now I'm just going to add them. So the net equation is going to be, so Zn ZnS plus, so a half plus just 1, that's 3/2, so that's this much oxygen, and then I don't have enough space. And now Z zinc oxide plus sulfur dioxide, this is the overall equation, the net equation, and this equation is the same as this equation, so whatever we did was correct. And now we just need to add these up. So the total enthalpy change is going to be 350.5 times -1. And I'm not going to write the units because they'll take a while. But however, I do recommend you to write down the units because your teacher may take off marks for that. And now therefore the enthalpy change of this reaction, if you add these all up, you should get -441.3 kilojoule. So this is the enthalpy change of this reaction here. And that's it for this video. So this is just a brief summary on how to solve the Hess's law problem. There are the lists there. If you want to take note, take it. And yeah, thanks for watching, and I'll see you.